In this video, we're going to do an extra example of optimization. So here we have a closed box with a square base and a surface area of 108 centimeters squared. And we want to know the maximum volume of the box. Okay, so first of all, let's just point out this word closed means that the box has a top. Okay, so there's a top of the box. And we know that it has a square base, okay? So if I was going to draw a picture, our box might look something like this. Okay, so because we know it has a square base, so we need some variables, okay? The things that we don't know are the length, the width, and the height of the box. Okay, but because it has a square base, the length and the width are both the same. Okay, so I'm going to call this x. Okay, so this side is actually equal to that side. Okay, and that side and that side. So we call that x, maybe. You can pick whatever you want. If you want to call it L for length, whatever. But we don't know the height, so the height might be different. So let's call that y. Okay, so then we want to maximize volume. So we want an equation for the volume. Okay, so for a box, the volume is equal to the length times the width times the height. So here, that's going to be x times y. So x squared times y. Okay, now this has too many variables, right? We have a v, an x, and a y. Okay, that's too many. We need to take the derivative, but we can't because there's so many variables. So we want to use this extra condition. Okay, so the surface area we know is 108. So this is going to give us our constraint that will help us eliminate one of the variables. Okay, so how do we compute the surface area? Okay, so surface area is the area of all the sides combined. Okay, now the bottom, okay, and the top, they're going to have the same area, whereas all the sides are going to have the same area. Okay, so when we compute the surface area, we're going to have a top and a bottom, so two of those, and the area is going to be x times x, so x squared. So this is for the top and the bottom. Okay, and this is their area. So there's two of them, and they have area x squared. And then to that I want to add, so there's 4 sides, and each side has area x times y. So this is the number of sides and the area for each. Okay, so our surface area is 2x squared plus 4xy. And we know the surface area is 108 centimeters squared. Go with centimeters, yeah. So we know that 108 is equal to 2x squared plus 4xy. Okay, so this is our constraint. Okay, so we want to take this and solve for one of the variables. Now, if I look at this equation, I see that there's x squared and x. It's going to be difficult to solve for x. So I think I want to solve this for y and replace y in the volume. Okay, so solve for y. So I'm going to have 4xy is equal to 108 minus 2x squared. And then if I divide by 4x, I'm going to have y is 108 minus 2x squared over 4x, which I could simplify to 54 minus x squared over 2x if I cancel out the 2. That's on the top and the bottom. Okay, so now what we're going to do is we're going to take this, okay, this is our y, and we're going to replace it in the volume equation. Okay, so the volume is equal to x squared times y. and y is 54 minus x squared over 2x. Okay, now there's an x on the bottom and two x's on the top, so one of them cancels. And then we can bring the x through, so this is going to be 54x minus x cubed all over 2, which we might want to reduce to 27x minus 1/2 x cubed, because that's going to be easier to take the derivative of. It doesn't look like we need the quotient rule anymore. So now I have the volume in terms of only x. Okay, so now we take the derivative. So v prime is going to be 27 minus 3 over 2 x squared. Okay, so we want to find the critical numbers. So we take our derivative, set it equal to 0. So that means 27 minus 3 over 2 x squared is equal to 0. If we solve for x squared, I get 3 over 2 x squared is equal to 27. So I'm going to times both sides by 2 over 3 to get rid of the 3 over 2. So then I have x squared is equal to 18, which means that x is equal to plus or minus the square root of 18. So it seems like we get two critical numbers, x equals negative, and root 18, this is 18 is 9 times 2. So this is going to be plus or minus 3 root 2 if we want to simplify. So x is going to be negative 3 root 2, or x is positive 3 root 2. Okay, but we want to think about what makes sense for the problem. Okay, so remember that x is the length of the sides on the bottom. So it doesn't make sense to have negative length. Okay, so this critical number, negative 3/2, it doesn't make sense. So we can't have a negative length. So this is not in the domain, which we can probably say is, I'm going to say bigger than 0, because if I have it equal to 0, then I don't have a box at all. Okay, which doesn't make sense either. Okay, now I also want to think about where my derivative does not exist, but it's a polynomial, so that never happens. So I don't have to worry about that. So that means our only critical number that makes sense, so the only critical number in our domain, is x equals 3 root 2, which is approximately 4.24. So we want to make sure that our absolute maximum occurs at this critical number. Oops. So we need to check this critical number gives the absolute max. So there's we want to think about how to do that. So there's only one critical number. So our domain, we think, is x bigger than 0. Okay, so the domain, the interval we're working on, is 0 to infinity. Okay, this is not closed. So that means that the extreme value theorem does not apply. So we have an open interval, but we only have one critical number. So we can use the critical point theorem we need to show x equals 3 root 2 is a relative max in order to show it is the absolute max. Okay, so using that, we only need to show it's a relative maximum. Now there's different ways you could do that. Maybe I'll do both of them here. So method 1 would be using the first derivative test. So this is looking for the increasing, decreasingness. So we'd make our table. So we'd have 3 root 2 here, which remember is approximately 4.24. So that's where the derivative is 0, and then we'd want to check a point on each side. So maybe we check, I don't know, 1, plug that into the derivative. So v prime of 1, now I need to remember what v prime looks like. So it's 27 minus 3 over 2 x squared. So this is 27 minus 3 over 2 times 1 squared. This is definitely a positive number, so we're increasing. And then if I check something bigger than 4, maybe 6. Okay, v prime of 6 is going to be 27 minus 3 over 2 times 36, or 6 squared. That number is going to be bigger than 27, so when I subtract it, I'm going to get a negative number, which means I'm decreasing, which means that this point is a relative maximum, which is what I wanted. So we know, so this implies x equals 3 root 2 is where the absolute max occurs. Okay, now method 2 is using the second derivative test. So here we want to take the second derivative. So when I do that, it's going to be negative 3 over 2 times 2x, right? Because it's 0, for the 27 is 0. And then I have the negative 3 over 2 times 2x, so this is negative 3x. So if I plug in my critical number, so my critical number, we can use this, maybe I should make a note here. So the derivative at my critical number is 0. Okay, so that's why I'm allowed to try to use this test. So when I plug this into the second derivative, I'm going to have negative 3 times 3 root 2. I don't actually care what this number is. It's a negative number. Okay, so if it's negative, that means that the graph is concave down. Okay, so that means our critical number has to actually be at the top. So that means x equals 3 over 2 is a relative maximum. So again, that means that we have found where the absolute max occurs. Okay, now, so we know that's where it is. Now let's go back and read the problem again. What was it actually looking for? We wanted the maximum volume. So we don't actually care what the dimensions of the box are. We just want to know what's the biggest volume we can make. So I know where it happens. Okay, so the max volume, oops. Maximum volume is going to be V of this critical number. Okay, now, maybe I'll use pink here. So because I'm plugging in only an X value, I'm going to use this version of my formula for V, right? This is V. If you wanted to use the original, okay, this one here, that's fine. You're just going to have to find Y first. Okay, so because I don't really need Y, I'm just going to go straight to using this one. So it's 27x. So 27 times 3 root 2 minus 1/2 times 3 root 2 cubed. Okay, and if you compute this, it's approximately 76.37, and then the units are going to be centimeters cubed. Okay, so that's the maximum volume we can achieve with a square base and surface area of 108 centimeters squared.